Okay, so we'll start now.
Yeah.
Okay, thank you for attending this lecture. Today I'm going to introduce a comparison amongst the traditional engines, engine car, hybrid vehicles, fuel cell vehicles, and pure electric vehicles. So here we show you the pure electric vehicles, the basic design and the major components. Okay, we can see the most important one, of course, is the battery pack, correct? So the electric energy is stored in this battery pack, correct? And the second major one is the electric engine. It is also electric motor, correct? So use a battery system to power the electric motor, and then the electric motor will drive the engine to drive the car to move. Okay, so for battery for electric vehicle, actually the design is pretty simple. However, can you notice that this battery pack actually is very big in size? Okay, actually it's bigger than the engine. Okay, the second one is the fuel cell vehicles or FCV. So compared with the electric vehicles, the fuel cell vehicles is more complicated. So you can see here, we have four major components. Okay, so first one is a fuel cell. Okay, usually it's a hydrogen fuel cell. Of course, we have methanol fuel cell and the hydrogen fuel cell and the other solid oxide fuel cell, correct? However, most commonly used fuel cell is a hydrogen fuel cell because of the energy density, the power density is higher than the rest. And for the vehicles, especially for the car, it's important to minimize the size of the power device, right? So hydrogen fuel cell is the first option compared with the solid oxide fuel cell and methanol fuel cell. And the second major component is a battery system, right? This is a battery system. And the third major component is the electric engine or the electric motor. And also hydrogen tank, usually gas fuel compressed hydrogen is stored in this hydrogen tank. Yeah, it's impossible to store in liquid fuel because if you want to convert into liquid fuel, then you have to cool down to minus 253 degrees C. Okay, so it's too low. As a result, for the transportation applications, for the land transportation, usually we use compressed hydrogen as a fuel. Okay, so here shows the basic schematic. So the power produced, the electric power produced by the fuel cell can use to charge the battery system. At the same time, also can directly use this electric power to power the electric engine or electric motor, correct? And also we can directly use both battery system and the fuel cell to power the electric engine. Okay, so by this way, we can increase the total power. Okay, can increase the total power, correct? So by the car can move faster. Okay. Okay, the next one is hybrid vehicles. Hybrid vehicles actually can be further divided into two categories. First one is hybrid electric vehicles or matched hybrids. Second one is plug-in hybrid electric vehicles. Okay, so can you tell me the difference between these two designs? The matched hybrids and the plug-in hybrid electric vehicles. What are the major difference? Can you tell me? Just based on this two schematic, can you tell me what is the difference between these two design?
Sir, in hybrid electric vehicle, we use both, sir, motor means battery as well as engine for the
Mm,
propulsion of the vehicle. Whereas plug-in
mm.
hybrid vehicles, sir, we use both engine and motor. But here the twist is we charge the battery from outside, external source. But in hybrid electric vehicle, we charge the battery by help of regeneration braking system.
Yeah, great. Yeah, very good. Okay, so you can see the difference. Yeah, very complete correct. Okay. So for this kind of design, we can see the engine. Actually, the engines the power produced by the engine can use to charge the battery system. Correct? Can charge the battery system, and at the same time, this engine also can power the transmission system. Correct? Transmission system. And for this kind of design, actually the only energy source is from the fuel. So we have only the fuel tank, correct? We can store the fuel, and there's no recharging plug, right? In this kind of design, we can see there's no circuit to charge the recharge the battery system. Instead, the battery system is recharged by the engine, correct? However, in this kind of design, we can see we have charging circuit. So this one, the battery system is recharged by the power grid. It is not charged by the engine. It is charged by the power grid. So we have to separate system, correct? The battery system is charged from the power grid, and this engine directly used to power the power the car, power the electric motor, correct? So we had these two are different in terms of design. Okay, the next one is SE vehicles or traditional combustion engine vehicles. So this one is very simple. We have only engine, okay, which can produce power to drive the car to move, correct? And yeah, maybe you guys can will ask, yeah, actually the S engine car also have battery system, correct? But that battery system is not used to power the electric motor. Instead, it is only used to start the engine. Okay, the battery system in this kind of traditional vehicles, the battery system only used to start the engine. It is not to power the vehicle. Okay, so all the power comes from this engine, from this IC engine. Okay. Okay, so here we summarize the electric vehicles. So in the United States and also the price. So most popular model is Tesla Model Y, and this year in 2021, the sold 172,000 units, and the market percentage is about 40.4%. The second popular one is Tesla Model 3, and the sold 128,000 units, and the market share is about 30%. All the rest actually are much lesser than these two models, correct? Then we can see the cost. Okay, the cost usually is from 35,000, 32,000 up to 43,000, and also has some more high luxury cars. For example, this one, Audi e-tron, and Porsche Taycan, and Tesla Model S, and also this one, Tesla Model X. Okay, so these are four types of electric car or high class vehicles. So they are much more expensive. So this car actually is adjusted cost, which means give some kind of incentive to promote the customers to purchase electric vehicle. So the government of USA give some incentive. Okay, so here shows the average cost for the electric vehicle is about 51,000. Okay, 51,000 US dollar. And after discount, or yeah, we'll take into the consideration the incentive, then the average cost is dropped to about 43.6 thousand US dollar. Okay, so next one is the fuel cell, the selling units and the price. So basically we have these three types of fuel cell vehicles. The first one is Toyota Mirai. Second one is Honda Clarity, and the last one is Hyundai Nexter. Okay, again, this Mirai has two models. The first one is XLE. The second one is Limited Okay. So the total units, so it's 2,629 units in the whole USA, and its market share is about 46%. So you can say XLE, the cost is about 50,000, okay, 50,000 US dollars, and this model is more expensive, about 76,000. Okay, the second popular model is Honda Clarity. Total sold 2,597, and the market share is about 46%, and the price is also for 59,000. It's almost the same. Okay. Okay, the next one is the Hyundai Nexon. So we can see the price is also quite close to the Honda Clarity. So here shows the average price for the fuel cell vehicle. So if you compare with this electric vehicle, so the fuel cell vehicle is more expensive. Okay, it's more expensive. Okay, the next one I want to introduce is fuel cost in USA. Actually, in USA, the fuel price is different at different states. Okay, for different states, the fuel price or fuel cost is different. The average fuel cost is about 4.164 US dollar per gallon. Okay, per gallon. And of course, this is only for 2021. Okay, at different years, okay, the price also can be different. Okay, compare with the hydrogen price. Okay, the gasoline is much cheaper, correct? The hydrogen we can see is about 16.47 US dollar per kg. This one is per gallon. Okay, so it's if you change it into kg, it is only is less than 2 US dollar per kg, correct? Okay, so here's a brief introduction on the electric vehicle fuel cost saving per year compared with the gas engines, compared with the combustion-based IC engines. Okay, so we can see at different states, okay, this fuel cost saving is different because just like I mentioned, different states the selling price of gas is different, correct? So in Nevada, case fuel costs can save by 1,220 US dollars per year, and in California can save about 1,200 US dollars. Washington, okay, it's about 1,178 US dollars. In Illinois, it's about 1,000 US dollar saving per year. Okay. Also in some other states, okay, the saving is also lesser. Okay, so the overall fuel cost saving is from 1,220 to 602 US dollars per year. Okay, compared with the traditional SE vehicles. Okay, just I have shown you the fuel cost saving for 1 year, correct? So in terms of lifetime fuel cost, so we have compared the battery electric vehicles and the hybrid plug-in hybrid vehicles, and together with compare with the SE vehicles. Okay, so this one is for pure battery electric vehicles, and this one is hybrid vehicles. Okay, and again, this one is for the pure electric vehicle, and this one is a hybrid vehicles. Okay, so similar to this one, but we have 3 different options. Okay, so first one is the least expensive charging option. Okay, which means the driver has very good practice or exercise. But this one is the typical charging behaviors. This is for the normal customers. And this one is a more expensive charging option. For example, you whenever you stop the car, then you recharge the vehicles. Okay, so this kind of charging habits can result in lots of energy losses. Okay, so the lifetime fuel cost saving actually is lesser. Okay, for this kind of charging option or charging habit. Okay, this one actually we can save the highest fuel cost for the lifetime. Okay, and also for different states, yes, the saving is different. For example, this is a RI. RI is a Rhode Island, and W is Washington, correct? Oh, sorry, it's Massachusetts. Okay, Massachusetts. Okay, so for different states, the fuel saving for lifetime also will be different. And the comparison and this one, the pure electric vehicle can save more than the hybrid vehicles, correct? Okay, so average can save 10,000, okay, 10,000 US dollars for the lifetime. And this hybrid vehicles can save about 9,000 US dollars the lifetime. Okay, so if the for normal customers or public, then usually okay, the savings is about 7,758 US dollars per life, and the hybrid vehicles about 7,200 US dollars per life. Okay. And this one average can save about 3,000, and this one can save 4,400 220 US dollars. Okay, so the next one is the estimated maintenance cost. Okay, because we know the capital cost is the major cost. However, the second one is the operating cost, the fuel cost, for example, and the maintenance cost. So we should take all these costs into consideration, correct? When you evaluate the overall performance of the different vehicles. Okay, so here show you the estimated maintenance cost for the first 50K miles. Then the maintenance fee for the SE engines is about 1,400 US dollar, and for the this one is the hybrid vehicles. Then can the maintenance cost is about 1,064 US dollars. And for electric vehicles, okay, the maintenance cost is the least. Okay, the lowest is only 577. And in the first 100K miles, okay, this is kind of the S engine car. The maintenance cost is about 4,400 US dollars. And same for hybrid is 2,600. And for the electric vehicle is about 2,000 US dollar. If for the lifetime, okay, assume the lifetime is 200K miles. Okay, so the SNG's maintenance cost is about 12,000, and this one about 6,000, and this one 6,300 US dollars. Okay, so if we compare the maintenance cost, actually the SE has the highest maintenance cost. Okay, the electric vehicles in most of the cases actually has the lowest maintenance cost. Okay, so here is a maintenance cost for a typical vehicles. Okay, this one Toyota SE vehicles. Okay, the maintenance cost is about 964.6 US dollars annually, and this one is 190 US dollar annually. Okay, so average is the electric vehicle is about 321 US dollars cheaper than average SE vehicles. Okay, the next one I want to compare the range of the pure electric vehicles can cover between two recharging. Okay, between two recharging. Okay, so first in the Tesla model Y. Okay, just like I mentioned, okay, the market share is about 40%, correct? Okay, this kind of electric vehicle can travel 44 to 326 miles every recharging. And the Tesla Model 3, the range is a little bit higher. It is about 263 miles to 353 miles. And okay, the rest also is only 140. This one, Nissan is the shortest one, can only cover about 149 to 226 miles every recharging. And then this one, Tesla Model S has the longest range, okay, can reach 402 miles per charging. Okay, the second best one is Tesla Model X, okay, can cover, the range can reach 271 miles. So the average range for all the electric vehicles is about 265 miles per charging. Okay. Okay. Now, I'm going to show you the range of fuel cell vehicles. Okay, so we have 5 types of fuel cell vehicles. Okay, first one is Toyota Marine Limited. Okay, the range is about 357 miles, and the Mirai XLE is 402 miles, and the Hyundai Nexo Limited 354, and Nexo Blue is 318, and Honda Clarity is 366. Okay, so the average is about 372. It is much higher than that of electric vehicle, correct? Electric vehicles is only 265, and this fuel cell vehicles can cover 372 miles. Okay. Okay, the next one I want to share with you guys is recharging stations in California. Okay, in California. Okay, so this one can tell us how convenient you can recharge your fuel tank or recharge your battery system. Okay, so for in California, okay, there are about 60 hydrogen refueling stations, and the gasoline stations about 8,492, and the EV chargers is about 75,000, and the EV supercharging stations are 5,000. Okay, so-called supercharging means the charging speed is faster. Okay, it's faster because the power is stronger. Okay, now I compile the hydrogen refueling stations in different countries. Okay, so first one is in Japan. There are totally 159 charging stations, and as we know, the land area in Japan is about 364,000 kilometers square, and so the density is about 4.26 units per 10 house to 5 kilometers square. Okay, so each station can only cover 2,293 kilometers. Okay, and in South Korea there are about 95 charging stations, and the land area is 97 kilometers square. So the density is 9.77. So each station need to cover 1,023 kilometers square. In Germany, there are 91 stations, and its land area is 348,000 kilometers square. So the density is only 2.61. So you can see each charging station should cover 3,830 kilometers. California, okay, so it's even less dense, okay, less dense because there are only 16 charging stations, and the land area is 403 kilometers square. So the density is only 1.49. So each station should cover 6,700 kilometers square. And in France, okay, it's even less dense. Okay, less dense. So there are only 41 charging stations, but France has a land area of 547,000 kilometers square. So which means each station should cover 30,000. Okay, 30,000 kilometers square. Okay, China, okay, is even less dense. Okay, because there are only 105 charging stations, but we know the area in China is much bigger than these countries, correct? Okay, then we compare with Singapore. Singapore's land area is only 733 kilometers square. So compare this one and this one, can see for the whole Singapore, yeah, there's only one charging stations. Okay, so you can see how scarce. Okay, how scarce this charging station. So it's very inconvenient. Okay, for the customers to recharge the hydrogen tank. Okay, so next is a battery. So the case efficiency, over efficiency by the different vehicles. Case the first one is a battery electric vehicle. Second one is a hydrogen fuel cell because the third one powered liquid conventional vehicles gives SE engines. Okay, so can see in this case, of course, we assume the electric power is produced from the solar energy from renewable electricity. Okay, so assuming this efficiency, efficiency is 100%. Okay, and in the transportation and the storage distribution, we are lose. Okay, we are lose 5% of the electric energy. Okay, so after that, the efficiency will drop to 95%. Then the inversion of AC to DC, because some of the vehicles is AC, some of the vehicles is DC charge. Okay, so again, this inversion will cause 5% energy losses, and again, the battery charging efficiency also will lose 5% energy. And again, there's inversion of DC to AC, again, will result in 5% energy losses. And again, the energy efficiency, engine efficiency, the electric motor from the battery to the electric motor, okay, there's another 10% energy loss. Okay, so overall, the efficiency is about 73%. Okay, about 73%. Okay, then compare the hydrogen fuel cell. So again, also 100% renewable energy electricity. Okay, then we use this electricity to produce hydrogen. So in this process, about 30% of energy will be lost. Okay, which means that from electricity to hydrogen, okay, the efficiency is about 70%. And the transportation, storage, and distribution of hydrogen, okay, will lose another 26%. So overall, okay, the efficiency is about 52% of fossil fuel production efficiency. Okay, about 52%. Okay, then for hydrogen to electricity, okay, the engine, assuming the fuel cell efficiency is about 50%, correct? So we lose another 50% of the remaining energy, right? And again, the DC to AC inversion, because the battery usually stored is AC, it's a DC, correct? You use the battery system to power the electric engine, then should be converted into AC, should convert into AC. So in this conversion from DC to AC, we have 5% energy loss. And again, the engine efficiency, the electric motor efficiency will be 90%. Okay, so we lose another 10%. So the overall efficiency is about 22% for the hydrogen fuel cell. Okay, so last one is SE engines. Okay, so fuel production efficiency about 44%. Okay, about 44%. And again, the engine efficiency is about 70%. Okay, so 70%. Okay, so the overall efficiency is 30%. It's a 30. Oh, okay, sorry, it's a 70% energy loss. It's only 30%. Okay, so the efficiency, the engine efficiency is only 30%. 30%. Okay, so of course this one for gasoline engine. Okay, for gasoline engine's efficiency is 30%, correct? For diesel engines, 45%. Okay, so 44% times 30%, then you can find out overall efficiency is about 13. Okay, 13%. Okay, here also you should be careful. Okay, this one is because we assuming use renewable electricity to produce diesel fuel or gasoline fuel, correct? So the efficiency is only 70%. And also we have CO2, air capture, and so on, and 37%, okay? But if you use the fossil fuel, okay, if you use fossil fuel, then we don't have this efficiency will be higher, correct? Okay, fossil fuel, okay, this fuel production efficiency will be higher, okay? Okay, so it's just assume for the electric vehicles, the energy comes from the renewable energy. However, if we use the electric power from the power plant, then gas operating efficiency of an electric vehicle will be much lower, correct? So typically we know the power plant has an efficiency of 40%, correct? So you can use 40% times 72%, okay? Times 72%, then will become 29%. Overall efficiency will be 29%. Because in this case, I assume is 100%, correct? But actually the efficiency of power plant is only 40%. Typical power plant, correct? So the overall efficiency will decrease significantly, okay? Even though, of course, still higher than fuel cell because higher than the SAE engine cost, correct? Okay, so here's a summary on the different vehicles. Okay, the first one is a battery electric vehicle. So the capital cost is moderate. Okay, it's moderate. It's higher than the S engine vehicles, but lower than the fuel cell vehicles, correct? And the operating cost is the lowest. Okay, it's cheap. It's the lowest, correct? Just now we have compared the different operating costs. Okay, here, correct? The estimate maintenance cost and also the fuel cost. Okay, so the lowest. Okay, so the lowest fuel cost and other maintenance cost is the lowest. Okay, so the BEV, the battery electric vehicles, the operating cost is the cheapest one, and the capital cost is in the middle. It's between the fuel cell vehicles and the SE vehicles. Okay, and also it's lesser. Okay, in terms of cost. Okay, so more expensive than the hybrid vehicles. Okay, than hybrid vehicles. Okay, so fuel cell vehicles, electric vehicles, the capital cost is more expensive, and the operating cost is moderate, and the hybrid vehicles is cheap in terms of capital cost, and hybrid case operating cost is more expensive. Case more expensive in terms of range. Case electric vehicle just I mentioned, average 263 miles, correct? So it is from low to moderate range. However, fuel cell electric vehicles is from moderate to high range. Okay, so average 270 something, correct? And hybrid vehicles has the highest range can be more than 400 miles. Okay, then the next one is the efficiency. Okay, if you just compare the, okay, so let me withdraw here. Okay, so okay, just I show you, okay, the efficiency is about 70%, and fuel cell vehicles, okay, the efficiency is about 20 to 30%, and the hybrid vehicles is about 20 to 25%. However, okay, this one is assumes the electricity is produced by renewable energy, correct? However, okay, if we use the electric the electricity produced by the power plant, okay, then the overall efficiency will be lower, correct? Okay, so it is about 25 to 35%. Okay, still higher than this one, and also higher than hybrid vehicles. Okay, so the next one is impacts on the environmental impacts. So the electric vehicles is least impacts because only electricity is used. Okay, for use renewable energy to produce electricity, then there's no emissions will be produced, correct? Fuel cell electric vehicles, okay, depends on the production of the hydrogen. Okay, if you use renewable energy to produce hydrogen, okay, then you can assume, okay, this kind of fuel cell vehicles also don't produce any carbon dioxide, correct? But still produce NOx, okay? No NOx, okay, because of fuel cell. Fuel cell is not the hydrogen engine, okay? So this one also don't produce any greenhouse gas emissions, okay? If we produce the squared hydrogen from the renewable energy. Okay, so last one is hybrid vehicles. This has a high impact because we still use petrol or diesel, correct? We still use petrol or diesel in the engines. Okay, so next one I want to share with you guys is a charging methodology. Okay, according to the comparison, it seems that electric vehicles is the best option. Okay, it's the best option because cleaner and the operating cost is lower. Also, the capital cost is in the middle, correct? It's it is more expensive than the Squad SNG hybrid. Okay, so cheaper than the fuel cell vehicles, correct? Okay, so the electric vehicle is the best option according to the comparison. Okay, now we'll introduce the charging methodology. Okay, so there are three types of charging methodology. Okay, so first one is conductive charging. This one is the most commonly charging methods. Okay, so most dominant and efficient form of charging technology. There are about 2.5 million public charging points worldwide. Okay, again, I should highlight, okay, this number is based on the data in 2021. Currently, okay, in 2024, much more charging points has been built. Yeah, especially in China. China is now the most advanced country in terms of electric vehicle applications. And the charging efficiency is about 95%. It has the highest charging efficiency and also highly regularized based at this AC. Okay, so next one is the inductive charging. Okay, so there's no direct wire to collect or cable to collect the vehicles and the power source, correct? So this one is by in contact charging, okay? Inductive charging. So this kind of charging method is more flexible and convenient. Okay, more flexible and convenient. However, there are no adoption numbers currently. It is still in trial phases. Okay. And the last one is battery swapping. Okay, this one is easy to understand. Okay. So this kind of method basically has a rapid way of recharging electric vehicles. Can be applied to multiple range of vehicles. Okay, so now I'm going to introduce the conductive charging. Okay, again, conductive charging can be further divided into two categories. First one is slow charging. Use AC charging. Okay, usually the charging power, we have three types of charging power. The first one is 7.4 kilowatts. The second one is 11 kilowatts, and the third one is 22 kilowatts. Okay, usually charged an electric vehicle from 0% to 100% takes about 6 hours. And okay, this kind of charging method is typically used for home or stop parking, where draining time is longer, correct? And most EVs AC charging are limited to 11 kilowatts charging, okay? So next one is fast charging or supercharging. Okay, so DC charging. Okay, so the charging power we have this is 4 types. Okay, basically it's 50 kilowatts, 80 kilowatts, 100 kilowatts, and 120 kilowatts. And the charging time has been significantly reduced to 1.5 hour or even shorter. Okay. Typically used for the urgent charge, whilst draining time is short. However, system charging methods has a higher burden on the electric infrastructure, correct? Because the power is very strong, so the infrastructure should be built strong, correct? Okay, the second one is inductive charging. Okay, so basically we use an onboard receiving pad and an external charging pad, okay, to transfer the electricity from the charging station to the vehicles. Okay, this kind of charging methods has efficiency of about 90%. Okay, have 90%. Okay, so here's the pros. The maintenance costs are lower and it's convenient and user-friendly. However, here's a shortcoming for this kind of charging methods is unable to batch fast charging without safety issues. Okay, so this kind of is more suitable for the slow charging. For the slow charging, it's not suitable for fast charging or supercharging. Okay. And also the setup cost is very high compared with the conductive charging. Because the capital cost is much more expensive. Okay, last one is battery swapping. Okay, battery swapping. Basically we have for the car, basically is button swapping. Okay, button swapping. So you can see we can swap the used battery, replace the flat battery with a newly charged battery, correct? Okay, so this kind of battery swap for the vehicles, for the car, actually not so convenient. It's not so convenient. Okay, need for automation, and this one requires a large maintenance cost structure, and the startup cost also is very expensive. Okay, very expensive. The next one is bus. For bus, usually we use top swapping. Okay, so which means that the battery is installed on the top of the bus. And as you can see, this battery system is about 2,000 kg. Okay, so it's much heavier than AC engines. Okay, AC engines to produce the same power, basically it's only a few hundred kg. Okay, a few hundred kg. So the battery system actually is very heavy, correct? Okay, so last one is a motorcycle. For motorcycle is easier. It's because the battery system is very small in size, and also it's very easier to change. You can the customer can do it by himself or herself. Okay, so this one is the easiest one. Okay. Okay, the last one I want to share with you guys is a vehicle to grid. Vehicle to grid. This one, vehicle to grid technology empowers them to feed energy back into the grid via the same chargers. Okay, because when after you run you drive the car and to a certain position and then come back, you notice that the battery system is still very full. So under the conditions, you can feed back part of the electric energy into the power grid. Okay, so this surplus power can serve diverse applications. Okay, and in turn, consumers receive compensation for their contributions. Okay, so this kind of technology is able to reduce the grid demand during the peak hours, correct? And to discharging the additional energy into the power grid. However, this kind of technology also has some shortcomings. The major shortcoming is the electric power. The electric vehicle battery system case lifetime will significantly reduced because you frequently charging, discharging, correct? So this one can easily destroy the battery system, correct? And also has serious energy leakage. Okay, this one can result in energy efficiency drop. Okay, so this kind of technology operation efficiency will be dropped to 53 to 70%. Okay, as we know, the charging efficiency for the conductive charging is 95%, correct? However, if we use this new technology, okay, then the overall efficiency will drop to 53 to 70%. Okay, so that's the end of this lectures. Yeah, so we still have a few minutes. Is there any questions?
Yes, participants, do you have any query?
Sir, I have a small query in fuel charging methodology, sir. Sir, how do the 2.7 million public charging points around the world impact the efficiency and adoption of conductive charging?
Okay, this is 2.7. Okay, this is the data in 2021. I think now has been increased to more than 10 million already. Okay, after 2 years, the total number charging points has increased to more than 10 million. So this is the data for 2021. Yeah, this is research actually was conducted by my previous students in 2021. Okay, I didn't update.
Okay, sir.
Okay.
Sir, I have
Any
one more
query?
question, sir.
Yeah, continue.
Sir, how does battery swapping impact the electric vehicle industry, especially in terms of speed and convenience?
You mean again? Can you repeat your question again?
I meant to ask, how does battery swapping impact the electric vehicle industry, especially in terms of speed and convenience, sir?
You mean the impact on the electric power grid?
Yes, sir.
Okay, yeah, of course, with the increase of electric vehicles, the demand for electric power will increase significantly. Okay, so you need to build more and more power plants, right? So this will definitely increase the course gas emissions produced by the CO2 emissions produced by the power plant. And however, okay, just like I mentioned, okay, if you compare the overall CO2 emissions, okay, the electric vehicles, yeah, because if you compare with the traditional SE engines, because SE engines produce a lot of CO2, correct? And also the efficiency is much lower. It's only 30%. Okay, so compare with this one, even we use the power plant to produce electricity, and the power plant also produce a lot of CO2. However, the overall efficiency is still higher than, okay, still higher than the SE vehicles. So overall, the greenhouse gas emissions produced by this electric vehicles will be lesser. So yeah, the only challenging, okay, for the countries, both governments actually is to invest a lot of money to build the charging stations, to build the infrastructures. Okay, so this one is a major challenge for the government.
Thank you, sir.
Okay, any more query from the participants? Sir, I have one query. That say there are two battery swapping stations are there in one city. The battery swapping station A, battery swapping station B. A is run by X company, B is run by Y company. Now, if the batteries are swapped between them, if A company battery is X company battery is given to Y, or Y company battery is given to X.
Mm.
Do you think
Okay.
any standardization is required in that case?
Okay, yeah, good question. Okay, so you should standardize the battery system. Okay, for a certain class of car or vehicles, then different companies will should design the battery system more or less should be the same. Okay, should be the same size. Okay, like the mobile phone and some other electric devices, right? Usually the batteries you can swap, right? So usually it's the same size, okay, for different devices, right? So that you can easily swapping, so can standardize the battery system. Of course, for the different class of vehicles, okay, the battery should be different because some for example the heavy duty vehicles, okay, the battery system should be more powerful, correct? But for the car, for the light duty vehicles, okay, then the battery system should be smaller. Okay, but for the same class, for example, okay, this is a company produces a small car and the weight maybe is 1000 kg, and the next company produces a similar car and the weight maybe heavier, okay, 1200. Okay, but for these two different companies, okay, for these two different cars, because they are close to each other, the mass is close to each other, so can still use the same battery system. Okay, so for easier swap, correct?
Yes. Sir, another query is that, say, I have, nowadays we are having different types of electricity tariffs, right? Say
Mm-hmm.
if I am purchasing electricity from coal power plant, it will have a certain tariff. If I am getting electricity from a solar resource, it will have another tariff. If I am getting from wind source, it may have another tariff.
Yeah,
So, say a particular
yes,
PV
yeah,
supplier,
definitely. Okay,
yeah,
yes, definitely there should be some kind of first thing you should have AC and DC inverter as I had just I had introduced. Okay. Secondly, because the different power source, the voltage will be different. Okay, so you should do some kind of adaptation. Okay, so that's the usually we use a different source we use to charge the battery system and store in the battery system. Then the battery system, we use the battery system to recharge the vehicles. Okay, so actually all the other end source will be used to charge the battery system. Also, the voltage, the power is different. Yeah, but there should be some kind of a connection or adapter to so that can works. Okay, actually in US we have one professor is doing this kind of work. Yeah, this professor is also from India, and he's working in the ECE, the electric and the school of electric and electronic engineering. Yeah, so he's doing this kind of integration work. Yeah, but myself, I'm not expert in this area. Yeah.
yeah. Say if a particular, I have a scooty, I have swapped a battery from a
Mm.
swapping station. It's fully charged.
Yeah.
Now I go to a power source where tariff is less. Say
Yes.
in
Correct.
the
Correct.
swapping station,
Yeah.
the
So there should
power,
be
yeah,
there should be a different plug,
yeah,
different circuit. Okay, should be a different circuit so that the power source, the power, okay, the charging power should be changed. For example, here we can see we have we have 7.4 kilowatts power and 11 kilowatts, 22 kilowatts. Okay, so for motorcycle applications, actually maybe this is a charging power is even lesser than this one. So there should be different charging circuit.
yes, yeah. Even I think the batteries which will be coming in next few years, they should have the provision to lock. Locking mechanism should be there. Otherwise, people where they will get the cheap electricity, they will charge the battery, and then they will run it, and ultimately the power companies, they will suffer these losses. There should
Yeah,
be a
correct.
smart locking mechanism for the batteries, so that
Mm.
it should be only be charged for designated companies only, not
Mm.
like at home or some other place where they get cheap electricity.
Mm. Yes. Yeah, correct.
Okay. So
Sir, one more
any
question,
question?
sir.
Yeah, in metal.
Actually, you only said, sir, means we'll be swapping the battery. Sir, suppose I am using a scooter and means same swapping battery system is there, and the swapping station is around suppose 30 kilometers, and I
Mm-hmm.
don't have any type of plug-in system to charge the battery.
Mm.
But company means every time I have for swapping the battery, for every time I have to go to 20 plus 20 40 kilometers up and down to
Mm.
swap my battery.
Yeah,
So
yeah,
is there
exactly.
any system?
Okay,
I
so
think you are
the
getting my point, sir.
yeah, so the motorcycle usually the range is very short. Yes, so that is more used for the because home use. Okay, for the city, maybe it's a short distance travel, cannot super for the long distance travel, and of course this one so swap the battery swapping is maybe potential solutions to this kind of issue. Because for batteries, motorcycles, the battery is very small in size, and the customer himself can change, okay, can exchange the battery system. Of course, okay, this one also has two category. The first one is a battery charge and swap stations. The second one is a battery swap, but store there, which means you swap the battery system, but you don't recharge. Okay, and the first one, you exchange the battery at same time. Also, this battery will be recharged in this power station, in this battery station. Yeah. So for this scooter applications, okay, currently actually there's no, this is only for trial. It's still under trial. Okay, it's not really used in practice because it's very challenging, right? Because one company don't have the course the sufficient form, okay, to install the swapping station everywhere, right? It's impossible for one company unless, okay, it is a nation a nation action. Okay, for example, the whole nation different connect all the schools, different companies together, and then ask them to standardize the battery system, correct? And contribute similar or the same share based on the market share. They contribute the same power station and so on. Unless can do like that, otherwise it's impractical.
Yes, sir. Thank you, sir. I hope, is there
Yeah,
any
thank you.
query from the participants?
Sir, I have one query, sir. Sir, how does battery swapping accommodate different vehicle ranges and battery types, sir?
Sorry, I didn't get you. Sorry.
Sir, I meant to ask, sir, how does battery swapping accommodate different vehicle ranges and different battery types, sir?
It means battery system compared with other types of vehicles.
Yes, sir. In different vehicles, how does, sir?
How much we can save?
Sir, like, sir, I meant to ask, for instance, a small car need one module, or a larger vehicle may use multiple modules, sir. But battery swapping accommodates have different ranges, na, sir. So how it's accommodate to different vehicle ranges?
Yeah, sir told you, na, there was a slide, sir told about different specifications of the batteries, like 11 kilowatt, 22
Mm-hmm.
kilowatt,
Mm.
7.5 kilowatt. So the ratings will of the particular vehicle will be dependent on the rating of the batteries. Okay.
Mm-hmm.
So if it's a scooty battery, maybe a 7 kilowatt battery is fine. If it is a
Mm-hmm.
uh, car, it can be a 11 kilowatt, maybe 1 or 2 batteries. So if it is a bus, maybe 22 kilowatt battery. So like that, it is not yet concrete nowadays. It is not yet standardized yet completely, because electric vehicle is yet to capture the market, and all at least 50% it should cross the market capture. Then only we can concretely we can tell that, okay, this much kilowatt battery should be applied for this type of vehicle for this type of range, like
Yes,
that.
yes, correct. Yeah, exactly. Yeah, for different batteries, the charging method should be charging power should be different. Usually, they will
Yes,
specify on the battery system on the vehicles. Okay, so they will tell you, okay, this one should be used what kind of charging power. Yeah, otherwise, okay, so you can burn the vehicles. For example, if the battery system is more like more suitable for the screen 11 kilowatts, for example. Yeah, if the vehicles gets suggest charging power is 11 kilowatts, then you use 22 kilowatts to charge. Okay, then we got problem. Okay, will become overheating, and the battery system can be burnt. Okay. Of course, if
yes,
for 11 kilowatts because you can use 7.4 kilowatts to charge. Okay, but the charging time will become longer.
exactly.
Okay, sir.
Okay,
Sir, one
thank you.
more question for curiosity. Sir, just last question, sir.
Okay, okay,
Hello.
Mrinmoy, quickly.
Sir, we are using electric EV vehicles for means we are thinking that yes, it is eco-friendly, it is environmental friendly, but ultimately we are charging the electric vehicle by the help of electricity, and electricity is mainly produced from power plants only, and
Yes.
power plant uses coal, right, sir? So
Yes.
ultimately, indirectly, we are using coal only, and we are burning fossil fuel here. We are burning fossil fuel at the power station. So
Yes.
ultimately, the result is same, sir. The earth
Yeah.
is one, sir, and the pollution is getting again and again. So what is the means? What is the benefit of using electric vehicle then, sir?
Okay. Yeah. Yeah. Very good job. Oh, very good question. Yeah. Okay. So just like I mentioned, actually, yeah. Here. Okay. Okay, so here assumes for the battery system, unless the battery the electric power is produced by the renewable energy, for example, solar power or solar energy, correct? Okay, then you assume okay, there's no CO2 emissions. However, if you produce from the power plant, like coal boiler system and biomass boiler, even biomass boiler system, or other types of power plant, for example, natural gas power plant, correct? So if you produce from this kind of a boiler system, then the efficiency will drop. Okay, will drop significantly. Okay, for example, the operating efficiency will become 25% to 35%, correct? But however, if you compare this one with the SE, okay, this is a hybrid vehicles. Okay, even compare with the hybrid vehicles, okay, this one is still higher than this one, correct? The overall efficiency is still higher than this one, which means less CO2 will be produced. Okay. However, if you compare with the pure SE engine, traditional SE engine vehicles, the overall efficiency is only 30%. Overall efficiency is only 30%, correct? And this one is 25. Okay. Okay, this one is 25 to 35%. Assume the mean is 30%. Okay, this one is 30%. We assume the power is produced from the coal boiler system, correct? So overall efficiency is still about 30%. But this one is only 13%, correct? So if we compare these two methods, okay, this one still more efficient, which means lesser CO2 will be produced to produce the same power, correct? Not understand now?
Understood, Mrinmoy, what sir told? If you are collecting electricity from coal power plant, it will give you efficiency hardly within 10% or 15%. But if you are using electric vehicle, using the electricity, the amount of efficiency will be higher. So in that case, it shows a lower carbon dioxide emission.
Mm.
Okay.
Okay, got it, sir. Got it, sir. Yes, sir. Got it, sir.
Okay, thank you.